PX4 and its integration with ROS2. And at the end of this, we will be teleoperating a drone in Gazebo with the help of this joystick. So in this, we will be using this joystick. You guys can use any joystick, whichever you have, PS4, wireless, wired, anything will work. Let me introduce myself formally. So my name is Kumar Utkarsh, and I am a research assistant at IIT Bombay, and I graduated this year. I was an electronics. My formal degree is in electronics and telecommunication engineering. However, I love to build cool robotics projects and IoT and edge AI devices. Besides that, I have also worked on many robotic projects, including AMRs, robotic arms, projects related to IoT, embedded systems, computer vision, and recently I've also started working on drones as well. So I would like to make a small announcement that this is one of the projects I have built. So this we call as Meccabot, and this is a two-wheel differential drive robot. It works entirely on ROS2 stack. It has a 2D LiDAR in it. It has a camera in it. It has LiPo batteries, IMU, Raspberry Pi, microcontrollers like ESP32 integrated in it. We have two motors with encoders. This is a full stack autonomous mobile robot which can perform autonomous docking, navigation, path planning, create the map of a room, everything. So I will be conducting a 45 days workshop or a 45 days training program to build this robot from scratch. In that, we will be covering entire ROS2 from basics, embedded systems, IoT, how to program microcontrollers, computer vision, and full stack integration. And on top of that, we will be also going in the non-technical skills as to how to build a cool LinkedIn profile, resume, how to get hired, how to pitch an interviewer. All these things will be covered. So if you guys are interested, I will drop a waitlist Google form in the comment section. You guys can join the waitlist and I'll reach out to you guys for the same. Okay. And it will be a paid program. It is very affordable considering the value that is being provided. So if you guys are interested, do join the waitlist. Also, I can have the recorded version of this, so I can have a second. Yes, definitely the recorded version will be available. Okay, so now let's begin with the workshop then. Okay. So why am I conducting this workshop? So recently I started working with drones. I thought of building a simulation in Gazebo. So when I started, then I found that the resources out there are very limited. Most of them are broken, outdated. I faced a lot of difficulty building a simple project. So I have been there and I found that there is a lot of scarcity of resources. You have a lot of resources on PX4 individually. You have limited resources on ROS2 individually, but there are no good resources for the integration of the two. So there is an integration gap. So my goal in this workshop is to, whatever frustration and experimentation I have gone through, I would like to give you guys a complete 3 hours roadmap using which you can build cool projects, which we will be looking in this workshop using drones. Okay. So who is this workshop for? This workshop is for students if you know the theory but don't know how to build real simulation-based projects or even hardware-based projects for that matter. But today we'll be looking at the simulation side. If you are ROS developers and you are comfortable with ROS2, but you don't have any idea about PX4 or MAVLink protocols, all those things, this workshop is for you. If you are a drone enthusiast and you want to move beyond manual control and give high-level commands to your drone using ROS2 so that your drone can do autonomous navigation using nav2, or you can attach a camera to your drone and it can follow a person or precisely land on a Ruko marker, all these things, You'll get to know the basics of things so you can implement all those things on your own. So this workshop is for you as well. So I would like to break down the 3 hours roadmap. So initially we will be starting with the setup and fundamentals. Then we will be looking at the theory as to what is ROS2, what is PX4. We will be clearing some common misconceptions. Yeah. So in this, we will be covering theory, and then we will have a 15 minutes break, and then we will move on to the hands-on coding session where we will be looking at what is off-board control and how to use it. And then finally, we will be looking at the final project, and then we will have a short Q&A session. Okay. So till now, you guys are cool. If you guys want to ask anything, just let me know before we begin. If we can begin, then just drop a yes in the chat box. Just try to be a little bit interactive. This time we have very less audience. I guess most people are not interested in drones. At least who are there, you just type a yes. Okay, cool. Then we will move forward. So let's see what is a drone. So till now, most of us knew, even I, when I was doing the research, I knew that drone is like the flying ones, the multi-rotor drones, single rotor, all these things. But I found out when I was reading the PX4 official documentation, this is the definition they mention for a drone. So a drone or unmanned vehicle, which is in short form, it's called UV. A drone or unmanned vehicle is an unmanned robotic vehicle that can manually or autonomously be controlled. Okay, so this is a drone, and drones are formally categorized into 4 main types, which is UAV, which stands for unmanned aerial vehicles, UGV, which stands for unmanned ground vehicles, USV, which stands for unmanned surface vehicles, and UUV for unmanned underwater vehicles. You can see the pictures here. So the first one, this picture is for UUV, underwater. This is for surface. This is the Curiosity rover. This also comes under the category of drone. This is sent by NASA to Mars. And these are the unmanned aerial vehicles, which are of many types. I have categorized here. I have put only 4 types: multi-rotor, fixed wings, single rotor, which is kind of a helicopter, and fixed wing hybrid VTOL. VTOL stands for vertical takeoff and landing. So it can take off vertically and even land vertically. Okay. So this was about what is a drone. So let's move forward. So now that we have seen what is a drone, let's see the technology stack we will be using in this workshop. So we will be using PX4 Autopilot. What is PX4 Autopilot? We will be looking at in detail. Basically, it is an open source flight control software. It handles stabilization, sensor fusion, safety, and a lot of things besides that. We will be looking at ROS2, specifically ROS2 Humble. So ROS2 is the high-level brain which we will be using, and we will be connecting a joystick to it, and we will try to control our drone using it. And we will be looking at something known as Micro XRCE DDS. We will be looking. So this is basically the translator, which will act as a translator for communication of PX4 with ROS2 Humble. We will be using this. So we will be looking at this in detail. Okay. So now we saw that there is one more word written here, PX4 Autopilot. So let's see what is an autopilot. So what is an autopilot? So basically, autopilot is the brain of the drone. Okay, so if we go to define autopilot, we can define autopilot as autopilot minimally consists of a flight stack software running on a real-time operating system on a flight controller hardware. So this can sound very confusing and complex when we are starting. So I'll break down these things. And if you just rewatch this once you have like understood other steps as well, then you will easily understand this. So what is a flight stack? So flight stack is basically guidance, navigation, and control algorithms. So PX4 is basically a flight stack or a firmware which has many algorithms like guidance, navigation, control algorithms, and many others as well. We will look at what are these things. And Autopilot runs on a real-time operating system and on a flight controller hardware. We will look at common misconceptions. What is a flight controller and what is PX4, the difference between the two. So why do we need an autopilot in the first place? It has inbuilt stabilization, it has safety features, and automates common tasks like landing, takeoff, executing predefined missions, etc. So why do we need an autopilot? Inbuilt stabilization. For example, let's consider that I am building a drone from scratch. I bought the frame of the drone. I bought 4 brushless motors, and I am about to build a drone. I have the flight controller, everything in place. Now, if I want to fly the drone, I'll have to do a lot of things in terms of PID, balancing, stabilization, everything. I'll have to write it manually on my own if I don't use PX4 firmware or flight controller. So PX4 handles all those things for me. So I can use PX4 out of the box and fly a drone just by giving high level commands that take off. So it will start taking off on its own. So one reason to use autopilot. Another is it has a lot of safety features. If you are building a drone, you just won't fly the drone. You will also have to integrate safety. For example, if you lose connection, then if there are no safety features, your drone will just fly away to some other land, or it will crash and cause accident, something. So you have to integrate safety features in the drone so that, for example, if there is some unwanted condition, drone goes back into fallback logic or panic mode and does few things to protect the drone, and it comes back to the ground. This the autopilot, PX4 autopilot, provides us. So one more reason to use it. And it automates common tasks like landing, takeoff, and executing predefined missions. If I want my drone to go to a specific coordinate in the 3D space, I just have to give the location, it will go there automatically. I don't have to do any coding for that. So these are few reasons why you use an autopilot. The autopilot, basically, if you drive a self-driving car, you manually drive it. But if it goes on autopilot, it does all the things on its own. Basically, that we refer to as autopilot. Okay. Till now, if you guys have any doubt, just let me know. And just let me know if I'm going too speed. So I'll just slow down a bit. Clear for now. Only Jijo is interested in the session, I guess. Guys, at least I'm not asking you to turn on your mic, at least write in the chat box. Okay, cool. Thumbs up will also work. Okay, it's fine. Clear. Then let's move forward then. So let's see now finally what is PX4 Autopilot. PX4 is a powerful open source autopilot flight stack running on Nutex RTOS. So there are many versions of RTOS. The most common versions which we may hear in day-to-day life is free RTOS. Okay. One of the recently popular RTOS, the RTOS which is getting very popular these days, is Zephyr. Okay. So PX4 runs on Nutex RTOS. Some key features of PX4 include it supports multi-vehicle types, like you can use PX4 not only to control your drones, but also to control ground vehicles, underwater vehicles, even the AMR, which I showed you guys at the beginning. You can use that AMR as well with PX4 and integrate that with PX4. So you can PX4 provides a lot of flight modes, right from offboard control to various other flight modes. PX4 also has safety features integrated in it, and it is an industrial grade firmware. One of the most important reasons of using PX4 is that it has deep integration with ROS2. So that is also very important. And it is very great at handling low-level commands. Like it handles very good sensor fusion, which is EKF, extended Kalman filter. Everything is like pre-done. It has built-in PID loops, built-in position and attitude control, etc. So attitude is nothing but orientation. And it makes very simple for users just to send high level commands, like if I want to move my drone forward, so I will just ask my drone, hey, move at 1 meter per second in the forward direction. So I am sending this high level command 1 meter per second in X direction forward. Now at the back end, PX4 is calculating all the things. It is calculating the pitch as to how much the drone has to tilt to start moving forward, what should be the rotor speed, and a lot of things, stabilization, safety, everything is being done by PX4. So basically, in a nutshell, PX4 is the firmware which we use to control drones out of the box. And it runs on a flight controller hardware, and also it runs on your laptop as well, which we will be looking at. We will be using two terms, SITL and HITL. We will be looking the difference at it, the difference of it. Okay. So basically, PX4 is a core part of broader platform that can include QGroundControl Station and Pixhawk hardware. Now, these are two words. When I was starting, I didn't have any idea what is PX4, are these jargon, QGroundControl, Pixhawk, what is GCS, what is ArduPilot, what is Mission Planner. All these things, these are very confusing for a beginner. So we will be looking at these one by one. So till now, we have seen that PX4 is a firmware autopilot for control. Now let's clear some common misconceptions. I was talking with few people, so when I was beginning, I used to use these terms interchangeably, PX4 and Pixhawk. So are PX4 and Pixhawk the same thing, or are they different? And what the hell is ArduPilot? What the hell is Mission Planner, QGroundControl, GCS? I don't know. So let's see what are they. So this is the first misconception to be cleared. PX4 not equal to Pixhawk. As we discussed just now, PX4 is the software that runs on a hardware. And Pixhawk, let's see the official definition of Pixhawk. So Pixhawk is a flight controller open hardware standard that can run PX4 Autopilot on it. What is it exactly? You guys can see these boards. These are not Pixhawk boards, but in a more refined way, you can say that these are Pixhawk based boards. Pixhawk is an open hardware standard used to build flight controllers. Taking the analogy of Arduino, you guys might be familiar with Arduino. Arduino is an open source platform. It provides all the circuit of Arduino. It's open source. Even I can download the Arduino circuit and build a custom Arduino board of my own. Basically, it's a standard. Similarly, PX4 Pixhawk is a standard for building flight controllers. So you guys, even when I was starting, I knew that this is Pixhawk, and I even used to call it PX4. But this is a Pixhawk based flight controller. We are aware of this specific board because these are the one which are mostly used by engineering students, because these are the most cheaply available ones. Although the cheaper ones are very expensive, but these are the cheaper ones which help us in building the project as per our needs. These are industrial grades. These are even more costlier. So PX4 can run on many flight controllers. Pixhawk is one of them. Okay, so Pixhawk is not a company. Pixhawk is a standard, and using these standards, company like Kuva, you can see Kuva here, you can see Holybro, companies like these, manufacturers like these use the standards to build their own flight controllers. You will see all these three are Pixhawk only, but different versions. Just like we have Arduino Uno. If I am starting as a beginner, I will go with Arduino Uno, just like I'll go with this Pixhawk board. If I have more pin requirements, more memory requirement, more speed maybe, then I will go with Arduino Mega. If I need a small form factor, then I will go with Arduino Nano, and so on. So based on that, we select these boards. based on our requirements. So this is a very big misconception, which I think it's cleared. If it's cleared, just write clear in the chat box. And if it's not clear, feel free to write not clear. I'll explain it once again. Okay, I think it is clear. Then let's move forward. Now let's look at what is GCS. So GCS stands for Ground Control Station and are ground-based systems that allow UV operators to monitor and control a drone and its payload. Payload can be any payload, maybe a gimbal camera on a drone can be considered as a payload. So I can use this software here, GCS here, ground control software. This will look like this to control my drone using GUI, graphical user interface, from the ground itself, from the ground station itself, and even control the payloads, camera, etc. So this is GCS, ground control station. What is QGround control? QGround control is a GCS software. GCS is a general term for a software like ground control station. QGround control is a GCS software. The name of the software is QGround control. So you can run QGround control on Windows, Linux, Mac, or even Android, and that QGround control communicates with PX4 via a protocol known as MAVLink. We won't be going into MAVLink because it is not relevant with ROS2, but if you are using hardcore PX4 only, then you will use a lot of MAVLink protocols. But in general, any GCS communicates with PX4 via MAVLink protocol. What is MAVLink? So MAVLink is a lightweight binary messaging protocol that allows efficient and easy communication between the drone and the GCS, the ground station. QGC is Q ground control. Desktop version are also used to flash PX4 firmware and configure PX4 on the flight controller hardware. So this software you are seeing here, this software is also used to flash the PX4 firmware onto the Pixhawk board or the flight controller hardware. And you are seeing this here, UAS. UAS stands for Unmanned Aerial System. So it includes unmanned aerial vehicle UAV plus GCS, ground control software. Combining that, we call it UAS. This was about GCS. Just give a thumbs up if it's clear. Cool. If there is any doubt, you can just unmute and ask. Initially, we will be covering a bit of theory just to clear all this jargon, and then we will be moving forward to the build. So let's move forward then. So this is the final end of confusion. This is one of the YouTube videos. I have picked this particular screen from a YouTube video, which I had referred to. So with this, all the confusions regarding drone keywords will be cleared. So here you can see three things: ground control software, flight controller firmware, and flight controller hardware. So you have heard terms like mission planner, Q ground control, APM planner, and other planners on Android phones. All these things come under ground control software. So basically they are ground control software via which we can control our drone using graphical user interface, and also using these softwares we can flash the firmware, which is PX4, onto the flight controller hardware. Here you can see flight controller hardware. Nowhere is Pixhawk mentioned. Although these are Pixhawk based boards and you will get Pixhawk mentioned somewhere in the name, but these are flight controller hardwares which are built on Pixhawk standard. And as we discussed, we can choose the board based on the requirements. If I'm building a very critical drone, for example, I have to launch a missile. So in that, the flight controller I'll use will be of very high grade, very high performance, very high speed. Then I'll be going for another flight controller. If I'm building an engineering project, then I'll be going for another flight controller. It may or may not be Pixhawk. These are flight controllers, QPilot, Holybro 6C, Matic wing boards, all these are there. And then we finally come to the firmware. There are two main firmwares broadly or commonly which are used. One is PX4 and one is ArduPilot. I have used PX4 because PX4 provides a very great integration with ROS2, and the documentation of PX4 is also good. So when you are using PX4, you generally use QGroundControl. So these two go together. When you are using ArduPilot, you generally use Mission Planner GCS. These go together. However, you can use any flight controller when you are building the real drone. So I hope the common misconceptions are clear till now. If you guys had any, if you guys were clear from beginning, then that's great. I was not clear. Inspired by DroneBot workshop. I have not like taken it from DroneBot. Maybe the person from whom I have taken, he might have taken from DroneBot. So, but anyways, um, okay, cool. Now let's see what PX4 SITL is and what is HITL. We will be looking at this SITL word when we will be launching our simulation in Gazebo. So beforehand only I'm explaining it. So SITL stands for software in the loop. When I run PX4 Autopilot, the physics engine, entire environment entirely on my laptop or my PC, no external hardware is there, then I call it SITL, software in the loop, PX4 SITL. For that, I just need a laptop. The PX4 firmware runs at the same speed of my laptop, and it is great for testing your drone's logic and for application development. This is PX4 SITL. When entire PX4 firmware I am running on my laptop itself, along with the physics and the environment, this whatever environment I have, my room and all those things, everything is on my laptop only. That is SITL. What is HITL? HITL stands for hardware in the loop. When I run the PX4 Autopilot not on my laptop but on the real flight controller, either on a Pixhawk board or any other flight controller. When I use PX4 on external flight controller and connect that flight controller with my laptop, then I call it HITL. That is physics, environment, everything is getting simulated in my laptop, but the actual PX4 firmware is running on the hardware, the flight controller. So with that, there is a laptop and a Pixhawk board. With that, we get to see the real-time performance of the Pixhawk board. Is it meeting the standards which I want? Is the speed requirements met? I can even connect the sensors. I can test the load, all those things. So when I need to test all those things, I connect, I go for HITL. Today, since we don't have Pixhawk, and also this is not in the scope of this video, this workshop, we will be looking at PX4 SITL, where we'll be running PX4 firmware entirely on our laptop. I think you guys have understood. Let's move forward then. Cool. Now let's come to our beloved friend ROS2. I think that most of you guys are familiar with ROS2. Just write yes in the chat box if you are familiar and no if you are not. Fully familiar. I like that confidence. Jamil. Yes. Yes. Yeah. Yes. Only Jijo seems uh, is not familiar. Okay, so we will cover ROS2 quickly in a nutshell. If you guys wish to see what is ROS2 and learn in depth, I have already pasted my YouTube channel link in the chat box. You can go there, watch. I have uploaded many videos covering the basics of ROS2, everything. You'll get familiar with ROS2, and then probably you can rewatch this video. However, I'll be covering just the theory part of it quickly, just to give an overview. Okay. Oh, and I hope you guys are in the WhatsApp community because all the updates are there. If not, to join the community as well. Now let's see what is ROS2 quickly. So ROS2 stands for Robot Operating System. It is a set of software libraries and tools for building robot applications. Okay, and ROS2 can be used with PX4 to create powerful drone applications. So why do we use ROS2 in first place? ROS2 has this slogan, don't reinvent the wheel. For example, if I were to build this robot, if I were to build this AMR from scratch, it would really have been a nightmare for me. You have to write your own mathematics, your own LiDAR code, your own algorithms, your own control loops, everything you have to write from scratch. But all thanks to ROS2, that ROS2 provides us a framework using which we can use certain pre-built packages to build such complex robots like this very easily. And once again, I would like to market this. If people who have joined new, I am teaching how to build this robot in a 45 days workshop. If you wish, you should join this. It will be a career accelerator, mainly very good for engineering students. Thank you. I quickly marketed it once again. So that's why we go for ROS2. ROS2 offers us scalability. For example, this is the mini version of my robot which I have built. Tomorrow, if I want to build a mega version of it, say a bigger version of it, or if I want to scale, I can use the entire same code, and I can just change the dimensions and make few changes in the URDF, and entire same code will work on any other robot similar to this. So ROS2 offers us scalability. ROS2 offers us reusability. We use packages in ROS2. For example, I have a computer vision package in this robot, the AMR. This same computer vision package, sorry, this same computer vision package I can use in my drone as well. That's an amazing reusability I'm getting. Better management and debugging. For example, I think it's very boring listening to the slides. Let's change the mood. For example, let's come here. For example, if I am building a robot and I have so many lines of code, one is for computer vision, one is for motor, one is for, say, LiDAR, and so on. All these codes I have written in a single file, maybe 5,000 or 10,000 lines of code. If any one of them stops working, for example, say computer vision got corrupted due to some reason, entire robot will collapse. Entire code will stop working. All thanks to ROS2, that it offers us something known as packages, wherein I can write computer vision nodes in this package. I can write motor control nodes or my controller nodes in this package. I can write my LiDAR node in another package, and I can run these nodes individually, and they will communicate with each other via something known as topics. Okay, so in case my CV node stops working, my robot will not stop working. Just one part of it will stop working, which is the computer vision node. My robot will still work fine. So this is the benefit that ROS2 offers us, which is better package management and debugging. For example, I want to debug something. I don't know where there is. I have to skim through 10,000 lines of code. This is again a nightmare. I know that computer vision node has stopped. I will simply go to the computer vision node, debug it, fix it, and my entire robot will start working once again. So that's the modularity ROS2 offers us. Going back to the PPT. Mm, cool. And we get to use nodes, which are nothing but blocks of program which communicate via other programs or other nodes via something known as ROS2 topics. How do nodes communicate? They send something known as ROS2 messages to ROS2 topics. Each message has a specific message type, which we need to keep in mind. Very important. We will be looking at PX4 message types. Then I'll be covering this in a bit detail, not very detail. We have services, we have QoS. QoS is something we will be looking at in today's session, and various other things. So this was a briefing about ROS2. If you guys have any doubt, let me know. Which is the best depth camera for drones? Not sure about the best one, but you can go with Intel depth cameras, one that comes for around 35 to 40K. I don't know the version, but they are very good depth cameras. Usually, people use Intel RealSense depth cameras only on drone. Even in IIT, there are many drones, so all of them are using that only. But yeah, everything is clear till now. Just a thumbs up or a yes in the chat box. Do I need to slow down a bit, or it's fine? Okay, it's fine. Then let's move forward. Now let's see PX4 plus ROS2. The PX4 uses Micro XRCE DDS middleware to allow micro orb messages to be published and subscribed on a companion computer as though they were ROS2 messages received on ROS2 topics and vice versa. Very complex statement. So let's break it down. As we discussed that this is the PX4 firmware, this is the ROS2 framework. If I want the communication to happen between the two, I will have to use a middleware or a translator. Middleware is Micro XRCE DDS agent. This is the bridge that translates ROS2 messages into micro orb messages. PX4 internally works on something known as micro orb messages. It also works on a publish subscribe model, and the micro orb messages are published to micro orb topics. But if I want to communicate, if I want ROS2 to communicate with PX4, I cannot directly send micro orb from ROS2. I will send ROS2 messages to ROS2 topics. From ROS2 topics, this middleware, the translator, will translate the message to the PX4 message type so that PX4 can understand, do the processing, then PX4 will send a reply. The loop continues. Okay, and there was one word, companion computer. What is a companion computer? For example, I'm building a drone. Okay, let's take the example of this again. For example, consider this as a drone. If you guys, I don't know if you guys can see, there is a Raspberry Pi here, attached here. So Raspberry Pi is nothing but a companion computer, and there is ESP32 attached here. So ESP32, you can consider it as the flight controller. Yeah. So ESP32, you can consider it as a flight controller. So on flight controller, my PX4 Autopilot firmware is running, and from my Raspberry Pi, I am sending high-level commands to my flight controller. So to the Raspberry Pi, I am referring to as companion computer. On companion computer, we do all the high-level processing. For example, if I am building a drone and I attach a 2D LiDAR on the drone, just like the one in my AMR. If I attach a 2D LiDAR on my drone and I connect the LiDAR to my Raspberry Pi, now the LiDAR is sending data to my Raspberry Pi. My Raspberry Pi is seeing, okay, there at these places, there are obstacles. So don't go from here, go from here. So it is sending commands, go left, go right. This is what a companion computer is doing. It is sending high-level commands to PX4. PX4 is breaking down that high-level command. Okay, companion computer has asked me to go left. So what should be my role? Pitch role? Yeah. What should my role? What should be my role so that I go towards the left? How much should I tilt? What should be my throttle? What should be my motor speed? What should the PWM, the PWM should be sent to the motor. All these things PS4 is taking care, the low level things. We can also take care of these things on our own manually, but we should only go in these kind of depths if we know what we are doing. If I don't know what is roll and I tweak roll, a drone will just go and collide somewhere. So it is better like start in order, start with high level, then initially go to low level. So this Micro XRCE, this provides a fast and reliable integration between PX4 and ROS2 and makes it much easier for ROS2 applications to get vehicle information and send commands. So you can get sensor information from the drone to ROS2, and you can also send high level commands back to the drone based on the information you got, all with the help of this Micro XRCE DDS. Let's see the basic architecture, what's happening behind the scene. Here you can see two things, PX4 Autopilot, and here you can see ROS2. And here you can see the Micro XRCE DDS. PX4 runs the client and ROS2 runs the agent. Okay, they communicate via UART, UDP, or TCP, whichever you can choose. So in PX4, there are micro orb topics which use micro orb messages. In ROS2, there are ROS2 nodes which send ROS2 messages to ROS2 topics. From ROS2 topics, this agent translates it and sends back to PX4 topics and vice versa. Loop continues. This is the architecture. What is DDS? Basically, DDS stands for Data Distribution Service. It is a networking architecture that ROS2 uses for fast and reliable communication and to move huge amounts of data at a very high speed between powerful computers. This basically DDS is a networking architecture on which ROS2 client libraries are built. So DDS is an industrial grade networking architecture. And Micro XRCE DDS is a lightweight translator that helps weak chips like PX4. Of course, PX4 is very weak compared to my laptop or anyone's laptop. So Micro XRCE DDS allows those kind of chips to communicate via the high-speed DDS network for communication and translation and all those things. That's why we use Micro XRCE DDS. Again, this is for DDS. So in older days, we used to use MAVROS, but now we don't use MAVROS, but we use DDS bridge, which is nothing but the Micro XRCE, wherein, for example, I am sending a trajectory set point message. We will look at what it is exactly. For example, ROS2 node is publishing a trajectory set point message, and Micro XRCE DDS is subscribing from it, converting it, and sending it to PX4. And then PX4 does the processing and sends whatever it needs to send back to ROS2 via the bridge. Basically, this is DDS. It's a translator, Micro XRCE. I hope you guys have understood. If you guys have any doubt, please let me know. Everyone can write a yes in the chat box. There are 29 people in the meet. I see only 2-3 hands coming up. And I does PX4 officially support ROS2 Jazzy? While I was going through the documentation, I didn't find Jazzy mentioned anywhere, but it should support because it will definitely support, because at the end of the day, we are using Micro XRC. Best it supports Humble, but I'm not sure, but it should support. You can try. If not, has anyone successfully integrated PX4 Micro XRC DDS, PX4 ROS-COM? You will see PX4 ROS-COM. PX4 ROS-COM is no more needed. It's outdated. ROS to Jazzy environment. Cool. Okay, I think everyone has understood. And I also hope that everyone is there. I don't think that anyone has gone to sleep. You should not Okay, cool. Now that we have seen enough theory, which is sufficient to get a good idea about what is drones, what is PX4, to remove common misconceptions like PX4 Pixhawk, what is ROS2, what is, how do they communicate, how to integrate them, what is GCS, what is mission planner, what is ArduPilot, what are flight controllers, how to choose them. All these things we have covered. Which is the best step for drone using ROS2? I just answered it. Now let's move on to the build. Before moving on to the build, let's see few more things, a few terms which we use, which we will be using. One of the terms is arm. Like I want to arm my drone. So arm is nothing but when I want my drone motors to get powered up and start spinning. If that happens, I say that my drone is armed. If I want to disarm my drone, I just cut off the power supply and drone goes into safe mode and drone motor stops spinning. That is disarm. Now the drone is completely safe. Takeoff is when I increase the throttle, drone lifts off from the ground and goes and hovers at a specific altitude. May or may not, but basically takeoff everyone understands, landing everyone understands. In PX4, PX4 takes care of all these things as we saw earlier. PX4 takes care of landing. If you just ask the drone to land, it will use a MAVLink command at the backend. It will do all the processing. It will slowly start descending at a constant velocity. It will start coming down. Moment it hits the ground, it identifies that okay, there is ground impact. I have hit the ground. Now let me disarm. It automatically disarms for you. You don't have to do anything. So all these things PX4 takes care for you. You just have to send high level commands to it. Um, Now that we are clear with all these things, there is the GitHub link provided. You can click here, but I'll not go here with this as I already have this. It's the page size. Maybe is it clearly visible to you guys? Okay. This is the final repository I have made, which you can simply download, clone it. Can you share the GitHub link? Okay. Can you quickly share the GitHub link? I've shared the GitHub link in the chat box. Okay. You can clone the repository. You can read the README here. I've tried to make a good README. However, if you guys find that there needs to be like something more needs to be added, please reach out to me personally. Just DM me. I'll update the README. And also, if you guys had attended the previous session, ROS to pick and place, if any one of you might have attended, just let me know that the GitHub is working fine or not, or it needs any update. If it's not, I'll update it. Okay. So in the README here, you will find all the steps as to how to set up this repository, system requirements, objectives, and here you can see. So we will be using the name as this PX4 ROS2 workspace. We will be using the name of this work. We will be naming our workspace this. Okay. And you use this command to clone because this has this tag here, recursive tag. Don't forget to use this tag or else this PX4 messages won't get cloned because this is a sub module. To clone a sub module, you must use the recursive tag. Okay, just follow this README. You have this ROS dep to update your all these things, and just follow this README and let me know if it's working fine or it needs some update. So let's begin with our this thing. So what we will do is I will uh, okay, let's make a new workspace itself. Let's go from scratch. Here I have, is the terminal visible to you clearly? Okay. Here I will, since I already have a PX4 ROS2 workspace in my home folder, I will name the workspace as PX4 workspace only. What I will do, mkdir PX4 underscore workspace. I'll create a new directory. I'll go inside PX4 underscore workspace. I'll do ls. There is nothing in here. I will create an src folder. I'll do ls. There is an src folder here. Now let's go inside the src folder. There is nothing in here. Now let's start following the steps mentioned here. First, First, let's see if we are just beginning. If you guys don't have ROS2 installed, you can simply copy paste and just copy this and paste it on your terminal here. ROS2 will get installed in your system. You can follow these steps. It will also get sourced automatically. This is the entire step you find in the ROS2 documentation. I have added in this one file only. Desktop version will get installed with ROS dev tools. Okay, so we have installed ROS. These are the few dependencies which you need to install for QGroundControl GCS. Just install this. Now here, you guys, I'm just showing the step because I already have these things set up. I'm just explaining how you can go about. So go to the home folder. Just type cd here. You are in the home folder now. Just clone this repository. Git clone px4 autopilot recursive. It will clone the PX4 autopilot repository. Then run this. Just copy this and run. It will happen, but you can do step by step also. Run this. It will set up the PX4 on your system. Then a PX4 directory will be created. Inside, you run this command. Make PX4 SITL. Here you are building the PX4 software in the loop. We discussed what is software in the loop, wherein you will be running the entire PX4 on your laptop or PC itself. This is very important to build the PX4 software in the loop setup on your host computer. Once this is done, open another terminal, source it, run this command. Let's start. Since I have all these things already done, I'll copy this. I'll paste it here. cd px4 autopilot. I am in my px4 directory. Now you didn't need to source px4 because it is not ROS. Just source the entire ROS, opt ROS, humble, all those things. I'll run this command. What this will do, make px4 SITL. Already this is getting made and built. And then this is the drone model which we will be using, GZX500. We will be using this drone. So PX4 has done everything for us. If I just enter this command, it will open Gazebo for us. No need to have a specific Gazebo installed on your system. When you do make PX4 SITL, automatically it will install the Gazebo which it has built in. And it will spawn the GZX500 drone. There are many drone variations, GZX500, GZX500 2D, which has a LiDAR on it. Maybe another can have a camera. We are using plain drone here just for teleoperation. If I press enter, you see it is running and it opens Gazebo for us. Okay, it opens Gazebo. In this, it spawns this drone for us. It feels very nice to see this drone for the first time. I felt very nice. Okay. There is this drone. Okay. Now, for example, I want to teleoperate this drone. Here you can see in the commander, it is saying, here in the commander, it is saying ready to take off. Now we will use these steps mentioned here. If you see here, you can see manual PX4 commands. You can use these commands, commander arm, commander takeoff, one by one. Don't copy paste entire thing. One by one, use it, and let's see what happens. So again, we will open the drone. Here in this terminal, I'll go here and I'll simply start typing, click the mouse and simply start typing Commander COMMANDER, Commander ARM. It should arm the drone. Here you can see my drone is armed. That is, power has been sent to my motors. Motors are spinning. Let's now, okay, now you see PX4 has built-in safety features. PX4 has built-in safety features. I armed my drone. Immediately I was supposed to ask it to take off, but I didn't. So PX4 waited for some time. It saw that no further command is coming, just disarm the drone. This is how PX4 works on autopilot. It does all the things on its own if you don't give it very specific instructions. That's why it is very difficult to control and build a project on offboard control from scratch. We will be looking at what is offboard control, but let's again do commander arm. Now it's arm. Now I'll quickly send commander takeoff. If I press this, you can see 2.5, it is showing altitude. Now my drone will go to an altitude of 2.5 meters. Here you can see 2.5 is mentioned, and just go and stop there. I didn't have to do anything. I just send the high level command PX to PX4. It armed it, it drone took off, it is hovering there. This is the benefit of using PX4. Now that it is flying now, I'll ask it to come down. Commander land. It will autonomously land. It will detect the ground. It will automatically disarm. You don't need to disarm. Disarmed by landing. This is the fallback logic, PX4 built-in logic, which it uses for safety. Again, I can do commander arm and it will fly, arm, and then I can do takeoff. It will fly, land, it will land. And if I do disarm, maybe it is already disarmed, but it won't do anything. But for example, if I do arm, then I do a disarm, so it stopped. If I do arm and then I do takeoff, and while I'm in takeoff, I do disarm. So it's not working. It says that it first needs to land, then only it will disarm. Because if I disarm it in midair, if I stop the motors, the drone will just fall down. So I'll have to land it and it will automatically disarm. Cool. Till here, you guys have any doubt, just let me know. Don't know. Okay. Cool. Then we, no doubt, all clear. Okay, cool, Janil. We will, one thing to keep in mind, very important, never close Gazebo like this. Never go here to the cross button and close Gazebo. It won't close Gazebo. Instances of it will remain open. Next time it won't open. You'll have to either do some manual things or restart your computer if you don't know how to do the manual things. Always go here in the terminal, press Control C. It's the best way. Okay. Now that we were able to set up PX4 software in the loop, we were able to not teleoperate, but control our drone using the PX4 itself. Now let's see how to control it via GCS, which in our case is QGC, Q ground control. I think it's clear. First, let's see how to set up QGC. To set up QGC, just go here and download the app image. Click on this link, QGroundControl. It will take you to the PX4 official documentation. If you guys need to know anything in detail, please refer this documentation. It is a great documentation, PX4 main official documentation. Whatever I have built reading this documentation. Few things are outdated, which I have updated in this GitHub repository. So that's fine. Depending on your system, Windows, Mac OS, all those things, you will go for, depending on the system you go, I'll go for Linux. Run this command in your terminal, copy this, paste it here. Just go to the home folder, paste it here, Then run these commands as well, paste it here. Although these are optional, I did it. Run these commands. These are important for setting up QGroundControl. Paste it here. Once all these things are done, click on download QGroundControl app image. Moment you click on it, download will start. It will go in your downloads folder, the app image. Follow this step. Go inside your downloads folder, CD downloads. Either you can come here. Once you have downloaded the app image, it will look like downloads. Then this will be there. You don't need to follow the step mentioned there, because there you'll have to add this manually. I have already added it. Just run this command chmod, staying in the home terminal, home page, run chmod plus x, this thing. So it will make the app image an executable. Then go to download, CD downloads. Then how do you run an executable? Dot slash executable name. Moment you do this, QGroundControl GUI will pop up. I am not doing this because I have created the executable. I have created a desktop icon for that executable. You need to follow certain steps to do that. I won't be doing this. I would be directly opening the QGroundControl from the icon itself. But you can follow these steps to open QGroundControl. So I have clicked on QGroundControl. Here you can see QGroundControl open. Here you can see disconnected, because QGroundControl is not yet connected to the PX4 firmware. Moment it will get connected, it will show ready to fly or connected. Using this is the GPS. Don't know of where. If someone is present in the meeting who lives here, let me know. I don't know this place. I think you can bring in your specific location. Yeah, include that was Africa, I guess. I stay in India. I will go to India. I will go to Mumbai. Where is Mumbai? Where is Mumbai, man? Okay, wherever is Mumbai, I'll go there, and my location will open. So you can use this, but this is not relevant in our case. I was just exploring. Okay. QGroundControl is there. We have opened QGroundControl. Now, once again, let's open. Let's go to PX4 Autopilot. Once again, let's run our simulation. Okay, my simulation is started. Got it. You guys didn't hear anything, but I heard in my headphone. It said hold flight mode. Even in your case, you'll hear it on your speaker. It has been connected to QGroundControl. And here you can see ready to fly. Now I can control my drone via this GUI. If I ask it to say arm, if I click on arm here and I slide this, it will arm. It said armed in my headphone. Okay. Now if I click on takeoff, now again if I slide this, it will start taking off, go, and it will go. Here you can see the meters. It is holding at 3 meters height. Here you can see it. Now if I want, where did my drone go? Yeah, now if I want to move my drone, I'll just right click here. For example, I'll right click here just close to it, and I'll ask it to go to this location. If I press, and if I slide the slide bar here, it will plan a path, and you're seeing it's going to that location. So this is what was meant by predefined mission, whatever the PPT had, mission set points or whatever. I just asked it to go to a specific place. It went there autonomously. I didn't have to do anything. That's what PX4 offers us. If I ask it to orbit at this location, it will start circling at this location. If I slide, You see, it's orbiting at this location. It will start moving like this. Here you can see. So this is how you can control the drone using the QGC, Q ground control. Now, if I just click on land, my drone will land here. And automatically it will disarm. You can even do recording from here. You can see the battery from here, and you can do many things here. If I just press Q, I guess there are a ton of things you can do in Q ground control. You can explore that like separately. This is a separate workshop altogether. It has so many features. Few we have looked at. Okay. How did you connect the Gazebo to SIM to QGC? I didn't do anything. Like I showed, I just launched the PX4 SITL. In that, I launched the drone. SITL launched Gazebo itself with the drone in it. I just launched Q ground control. I showed how you guys can launch it. Q ground control turned on. There is some internal communication. It got connected via MAVLink protocol. They are communicating, and the drone is flying. There is nothing much I have done till now. Still, I see everyone is not writing, but anyways, we will now close this, and we will close. You can close Q ground control like this from here only, no problem. But if you are starting from terminal, try to close it from terminal. I started from the desktop icon, so I have closed it manually. Okay, now we have covered this. Let's see what's there after this. So we were able to arm our drone. We were able to take off, landing, everything. All this we did using Q ground control and all those things. We did the environment setup. We saw how to set up ROS2 Humble on your system. We saw how to install PX4 Autopilot SITL. We saw how to set up Q ground control, and we also teleoperated our drone graphically using Q ground control and PX4 Autopilot. Let's move forward now. Am I missing something? We were able to do that. Offboard mode. Okay, one thing I'm missing. I'll quickly cover that. Now we saw how to control our drone using graphical user interface like QGC, Q ground control. Let's try and implement Micro XRCE DDS agent now, wherein we will try to get sensor information of the drone, the simulated sensor information, to our ROS2 topics. Let's do that. How will we do that? We will go to the home folder. Here you can see these are the steps mentioned for installing Micro XRCE DDS agent. Open a terminal. You just copy this step, git clone Micro XRCE DDS agent in git. Then it will create a directory named as this. Inside the directory, go and build the directory. Copy these steps. Just these are the steps you have to follow. Once everything is done, then do what I'm doing. Open 3 terminals. How did I open 3 terminals? I pressed Ctrl Shift O. Open 3 terminals. In one terminal, go to PX4 Autopilot. In another terminal, once you have set up the Micro XRCE DDS agent, go to the Micro XRCE DDS agent. And in another terminal, you'll do one thing which we will look at. Okay, let's try this first, then we will do the workspace thing. So in Micro XRCE DDS agent, once you have set this up, use this command This will start the agent, the translator, which will translate the PX4 autopilot message and the ROS2 message. Let's start Gazebo simulation. I have started the Gazebo simulation here. Drone has started, ready to take off. Now I'll start the agent here. Now you can see the agent got connected. Now, okay, let's close the agent now. I have disconnected the agent. Now I only have this drone and this Gazebo. If I do here ROS2 topic list, I see nothing. There are no topics. These are just internal ROS topics. There are no topics related to my drone in Gazebo. Okay. I start the agent once again. My agent got started. Once again, if I try to do ROS2 topic list, okay, I think that I'll have to restart this once again. Once the agent gets disconnected, it doesn't connect again if you don't restart it. And start the agent. Source. Let's see. I get a topic list. Yeah, you have to source the terminal once again so that it gets fresh updates. Here you can see now that I get in my ROS2. What here you can see in the first terminal. In this terminal, I am running PX4 SITL, this drone and simulator. In the middle terminal, I am running the translator. And in the last terminal, I am running ROS2 topic list. Here you can see, I can see so many topics related to the drone, all in my ROS2, all thanks to Micro XRCE DDS agent. We have actuator, motor. This in stands for input. I will send high level commands to PX4 via the agent. So PX4 will be subscribing from these topics. This is in. And this out stands for PX4 will send me ROS2 commands like battery status. So ROS2 will be subscribing from PX4. I see so many topics related to drone like vehicle control mode, GPS position, local position V1, and all these things. So now our agent is working fine. Let's do some few more things. Let's try to see. We can only use the out command, that is PX4 is publishing to us, ROS2 will subscribe. So let's try to see what is there inside vehicle local position V1. Let's try, we can see it or not. ROS2 topic echo FMU out vehicle local position V1. You see this message? PX4 messages message vehicle location position invalid. I'm not able to read the message. I am not able to read the topics. Why is it happening? Because I haven't installed this package. This package contains all the translations, all the PX4 messages which PX4 uses, micro-org messages, which has been translated for ROS in terms of ROS2 messages. So you have to install this package first. So let's do that, or else I won't be able to see. If I do a ROS2 topic info and I want to see what is vehicle status V1, what's the message type? FMU out vehicle status V1. You can see the message type is this. Publisher is one, that is PX4 is publishing to this topic. No one is subscribing yet. ROS2 is supposed to subscribe from it. Let's set up the messages package for now. If you guys have any doubt, just let me know. PX4 Autopilot taking so much time. Yes, it will take time. It is a very big software. Clear till now, till here? Clear. Okay. Let's now set up the PX4 messages. How do we set up that? Let's clear these. And here we just created a PX4 underscore workspace. So I'll go inside my PX4 underscore workspace. Inside that, I'll go inside my SRC folder. Right now, there is nothing here. I'll simply go and clone this package. Let's go to PX4 messages, GitHub, Repo. This is the one which I'm talking about. I think I haven't added the link to it, but we'll be installing the main branch only. Git clone. I'll clone this repository. Okay. So here inside the PX4 workspace, I will do git clone PX4 messages. It got cloned. Now if I do ls, there is this PX4 messages. Now if I source the workspace, I'll go back inside my workspace. If I first let me build the workspace. So cb Falcon build. It might take some time because it is a very big package. So with the help of this package, now my ROS2 environment will recognize that there are something known as PX4 messages. Now it should be able to read from ROS2 topics. Okay, I think this might take a lot of time. So for now, I'll go to my other workspace, which I was working on till now. That is PX4 ROS2 workspace. I have already cloned it, so no need to. I have already built it, so no need to build. Here you can see PX4 messages. I'll go back and I'll once again start the SITL. And I will start the DDS agent. DDS agent is started. Now let me source the environment once. Source install setup.bash. Now this workspace has the PX4 messages packages. The above one is getting built, below one has it. So now it should be able to read the ROS2 topic data. ROS2 topic list. Now let me try reading vehicle status V1. So ROS2 topic echo. Let's read FMU in vehicle status. Why is it not coming? Vehicle. Okay. It's out. It's out. It's not in. FMU out. Vehicle status V1. Now it should give me the vehicle status values. Now you can see that I am getting the data. It is showing me the vehicle status, system ID, component, safety, off, all these things I'm getting. So here PX4 SITL is sending the data via Micro XRCE DDS agent to my ROS2 topic, and I'm able to read it. Why? Because I'm using PX4 message in this workspace. If you are not using, then you won't be able to get. So right now I'm able to read the data. Right now I'm successfully able to read the data from my drone in the simulation using ROS2, but I cannot write the data directly using terminal. Why? Because for writing the data, I need to go in offboard mode. So let's see what is offboard mode. Till here, is everything clear? Still getting built. I'll close this. Now let's go back to the PPT once again and see what is offboard mode. So let's see what is offboard mode and why do we need that. So we have ROS2. PX4 is great at controlling drone at low level. We have seen how is it great. everything it does on its own. We just need to send high level commands or decisions. And we use ROS2 to process complex sensor information like computer vision data or joystick data or LiDAR data. And we do all the processing in ROS2 only and just send the high level commands for PX4 to do the low level processing. Okay. Offboard control. What is offboard control? Till now, PX4 is very strict about this offboard control. It won't give the drone control in your hands so easily. You have to do a lot of things to get the control of the drone in your hands. You so that PX4 offboard it's to you. So offboard control is a special flight mode in PX4. It tells the flight controller that ignore your internal sensor states and internal readings, all those things, and listen to the external data stream coming from the controller or ROS2 or companion computer or high level user. Just offboard the control to the user. Don't do anything on your own. This is basically offboard control. Let's see how do we configure offboard control in PX4. This is very critical and gives a lot of errors if you don't do anything right. When a bit of error mistake and it won't go into offboard control. Every time it will go in manual control and PX4 will do the all the handling. So there are three pillars of offboard control. You have to make sure three things are right for your drone to go in offboard control. So to successfully take control of PX4 drone using ROS2, you must satisfy three strict requirements simultaneously. If any pillar or requirement fails, the drone will reject your command and trigger fallback logic and go in panic mode or fail-safe mode, wherein drone PX4 will take all the control and the drone will start landing and will disarm. Okay, so three pillars are there. First pillar is quality of service. We will look at it, what it is. Second is the heartbeat for offboard control mode. And third is continuous trajectory set points. We will look at these three in detail. Let's go. Let's see what is quality of service. This is a general ROS topic. When you write a subscriber, create publisher, create subscription, when you write that, you often don't mention the quality of service. You just mention depth equal to 1. QoS is not mentioned. So ROS takes it by default. But in here, when we are using PX4, we need to specifically mention the QoS. Let's see what is QoS. QoS stands for quality of service. It is a feature that allows developers to customize and control how messages are transported between nodes. What does that mean? For example, if let's see the example here only what it is mentioned. For example, PX4 sends sensor data via UDP. UDP is a communication protocol. PX4 sends sensor data via UDP, and if you at the other end are listening using TCP, like UDP is best effort. It is a quality of service policy which I'll explain. PX4 is sending data at say best effort, and you are listening to say at reliable, there won't be any communication, just the data will get dropped. So it best effort or UDP, it doesn't care if a packet is missed. PX4 will continuously keep on sending the drone status continuously to ROS2. It doesn't care ROS2 is receiving it or a packet is getting missed. But if ROS2 is set in a mode that I want each and every packet, no packet needs to be missed, it won't be able to catch the data. Both the users should be on the same frequency to catch the data. Same agreement that if data gets missed, leave it, catch the next data. So that is best effort. I want each and every data. Don't want any data to be missed. That is reliable policy. So PX4 by default sends at best effort. And so here you can see there are three quality of service policies. I don't know if it's visible or not, but there is this one thing, reliability, another is history, third is durability. Reliability has two types, reliable and best effort. PX4 uses best effort. History how many last messages do you want in buffer? Last 10, last 1000, last one, all. So PX4, here you can see, while here we are in the code, here we are defining the quality of service profile. In the reliability policy, I am giving best effort because PX4 works on that. In durability, in history, I am giving keep last. I only want the last message. I am not concerned about the last 10 positions of the drone. I only want the current position. So the last message. Durability is of two types, volatile and transient local. PX4 sends on transient local. Transient local is used for transmitting critical data, and best effort again is used for sending high frequency data. And history is history. Like how many data you want. I want only one data. Depth is again the buffer size. Depth I want one. Since I only need one data, I have kept the buffer as one. You can also keep it as 5 or 10, doesn't matter. Not that important. These three are very important: reliability, durability, and history. These things are not set right, communication won't get established. So for messages to be delivered, the QoS policies of publisher and subscriber must be compatible. We discussed it. So the rule is, if PX4 publishes best effort, your ROS2 node must subscribe as best effort. If you use reliable, they won't connect. So basically, this is nothing but compatibility. I am sending at this compatibility, you also receive at this compatibility, or else we won't be able to connect. This is quality of service, one of the very important pillars for offboard control. I hope it was clear. Guys, at least do the little effort of typing yes, no. If not clear, then just let me know the doubt, what is not clear. Not sleeping, okay. That's good. Uh, I think that this is not a very popular topic. We only have 15, 16 people, although a lot of them had registered. Alive. Great. Great that you are alive. Okay. Let's look at the second pillar. Sorry. Let's look at the second pillar. These things, since we haven't seen any problem and I'm directly giving you guys the solution, so it the importance you'll not get to know, but when you go to code, you might get to know the importance. Uh, these are the three things that I'm directly providing you the solution without the problem. Might feel boring at first, but these are very critical. The second pillar is the heartbeat. This is a safety mechanism. PX4 needs a proof of life from your computer, just as I need from you guys, that you guys are alive. Just keep on giving me a proof of life, a heartbeat at every, say, after every 5 minutes frequency. Uh, just like that, PX4 requires a heartbeat so that it knows that someone out there is there who is taking care of the drone in offboard mode. So if your code, so how do you provide this heartbeat? PX4 expects that this offboard control message type, this offboard control message type, you keep on sending it at a frequency of 2 hertz or greater. That is, after every 0.5 seconds or less than that, less than every 0.5 seconds, you keep on sending, publishing a heartbeat that, okay, I am alive. A companion computer or a user outside PX4 is there who is taking care of the drone. So if your code crashes, this stream stops. PX4 detects the silence for greater than 0.5 seconds. That is, the heartbeat drops below 2 hertz. Then PX4 immediately triggers the failsafe, and then again it comes back to manual mode. No more offboard mode. You won't be able to control the drone. So it needs a proof of life at a frequency of greater than 2 hertz. 10 hertz, 20 hertz, 100 hertz, anything would do. Just that it needs that, okay, someone is there. This offboard control heartbeat message tells PX4 what to listen. By setting position true, you disable the internal GPS and enable external position control. Here we are defining the heartbeat function. This function is called at a rate of 10 hertz, for example. And here we are setting position as true. In this case, since we will be using position control, for now. Then we will be moving on to velocity control. So in this case, I am sending that, asking PX4 that come in offboard mode, and I'll send you position command and you execute that. So this was the second pillar, offboard mode. For switching to offboard mode, that is getting control in our hands to control the drone using ROS2. Let's see the final pillar. Once PX4 comes in offboard mode, it sees that heartbeat is there. Immediately, it should get continuous set points, trajectory set points as to which position it is supposed to go or at what velocity it is supposed to go. So you cannot stay in offboard mode if the drone doesn't know where to go. Moment you switch to offboard mode, at that moment only you should flood the drone continuously with go there, go there, go there, go there. It's not that offboard mode, it got switched, then you asked once, okay, go there, and then you slept. Drone won't go there, it will come to manual mode. You have to continuously keep on reminding them, just like I'm reminding you guys, stay awake, stay alive. Continuously you have to remind the what do you call, drone, PX4, that go there, go there, go there, go there, go to 5 meters. So PX4 will see that okay, heartbeat is there and someone is continuously asking me to go there. So this is the third pillar, which will keep you in offboard mode, or else your mode will get switched back to manual. PX4 checks its buffer if valid set point data are waiting. If you tell so many times, it will show in buffer. It will see that okay, there is data. It will go there. If it moment it finds that there is no data, it will go in panic mode. It sees that heartbeat is there, but no one is commanding me where to go. I think the driver is confused. Just let's go back to manual mode and land. This is what PX4 does. So if the buffer is empty, the mode switch is not sustained. PX4 enters failsafe mode and continue. Even if continuous heartbeat signal is there, it will land. These are the code snippets which we will be looking at, but just for example, I am explaining here only. Publish position set point. I'm sorry. Publish position set point. Set point is nothing but um, uh, where I'm supposed to go in terms of position, or what my speed is supposed to be in terms of velocity. That is set point. Here, since we are in position control mode, I am giving the drone XYZ. Okay, message trajectory set point. It is a message type. Position, I am asking go to XYZ. Yaw. What does yaw mean? We will be looking at it. I guess in the next slide. Yeah, here only. I'll go back to the previous slide. Let me explain what is yaw. Here you can see PX4 ROS2 frame transformation. Okay. So PX4 works on something known as NED framework, north, east, down. That is, x-axis is in north direction, y-axis is in east direction, that is to the right of north, and z-axis is facing downwards, just like you can see here, north, east, down. So this will be more relevant. If I want my drone to move forward, I will have to rotate my drone in y-axis. So this is called pitch. So if I will pitch my drone, it will go forward or it will go backward. If I roll my drone, that is rotate about x-axis, it will go left or it will go right. If I rotate my drone about the y-axis, that is called yaw. It will rotate about the y-axis and it will take angular turns. That is yaw. So this was about frame transformations. We will look at these two as well. ROS works specifically on ENU. PX4 works on NED, northeast down. Here you can see. We will be looking at something known as FLU, front left up, to get an intuitive control of the drone. We will be looking at it. Why do we need that? But so here I am giving yaw as 90 degree. That is, I'm asking my drone to turn by I'm asking my drone to turn by 90 degrees while flying. And here I'm giving timestamps. This is the basic structure of the message you can see. And then I am publishing the trajectory set point. Okay. And this is the timer callback, which is being called at a rate of 10 hertz. That is after every 0.1 seconds. So that heartbeat is there. So here you can see publish offboard control heartbeat. There is a function which is continuously publishing offboard control message to PX4. That is okay. I am there. Heartbeat is there. Then look at this. Here I have self offboard set point counter, and when counter is not 1, it is going here and it is like step up is happening. Why am I doing this? So this is known as warming up PX4. I'm warming up PX4. Why do I need this? It uh, if I just start the timer callback, and if I set just one signal and ask PX4 to switch to offboard mode, it won't switch uh, just on the basis of one signal. Initially, you have to send a few signals to PX4 to see a continuous stream that, okay, the user is there. Once it sees a continuous stream, that is, once I have sent 9 heartbeat signals, in the 10th signal, I'll ask PX4, okay, now engage offboard mode. I'll send the request. My request will get accepted. I'll get in offboard mode and I'll ask the drone to arm. Once the drone is armed, now using this command, publish position set point, using this function, from the ROS2 node itself, I will be able to fly the drone. So in publish position set point, I am sending X as 0, Y as 0. That is, my drone will not go forward nor sideways. I'm only sending takeoff height, which I have given as 5 meters. So my drone will go up at 5 meters and stop there. Now here, the moment it sees that I have reached 5 meters, it will activate the landing sequence and it will land and the program will exit. This is just to explain trajectory set point, that once offboard mode is engaged and you are checking that drone is at ground and offboard mode is engaged, navigation state offboard, continuously send trajectory messages. Continuously, drone will start flying 0.1, 0.2, and I'm asking go to 555. Then you're understanding things will, a closed loop system is happening, wherein PX4 is sending, okay, right now I'm here, I have to go here, and I am telling go here. So it's a closed loop system. This was about trajectory set point code. I'll be explaining once I open VS Code. But just to keep in mind, QoS profile, you have to make it sure it's compatible. Continuously publish heartbeat. Once heartbeat is continuously published, once offboard is engaged, continuously publish set point. And your drone will be in offboard mode. Moment any one of them stop, mainly heartbeat or trajectory set point, drone will come in fail safe, will land. I hope this is clear. If you guys have any doubt, just let me know. Everyone is clear? Okay, cool. Then let's implement this on. Okay. So for that, we will go here. I'm assuming that in this workshop, people are very good with ROS. They know how to create packages and all those things. So I'm not going in depth like this one I did, created a workspace and package. I'm simply explaining the code which I have done till now in my package. If you guys aren't that familiar with creating packages, you can refer my previous workshops where I have done everything from scratch. Implement that in this workshop, or else it will become too long already. We are running late. Okay, so I will just close this PX4 workspace. I will remove it rather. Okay, I have removed the PX4 workspace. I already have this PX4 ROS2 workspace built in, and I will now open VS Code. How will you open that? Code space dot, enter. Why is it not opening? Let's go in SRC and open it. Code space dot. Okay, now it is open. Here you can see, we will look at all these things. But here I have 3 packages. One of them I have cloned PX4 messages package. Let's quickly see what is inside PX4 messages. Here are so many message types you can see. These are the message types you can see. So in here, we will see trajectory set point message type. Before that, let's see offboard control message type. So here, can you see that in the offboard control, you have this, you have timestamp, velocity, that is, do I want to use velocity, true or false, boolean. Do I want to use position or velocity or acceleration or attitude, whatever I want to use, I can send that to the offboard control, that hey, come to offboard control and give me access for position. Don't listen to your internal position states, listen to my positions. In here right now we are using position, but while controlling it with joystick, we will be using velocity. This was the offboard control message type. Let's see trajectory control message type. These are all pre-built by PX4 itself, I guess. Trajectory set point. This is a big file. No, it's short. So in trajectory set point, here you can see it is using NED frame. So whenever I am publishing trajectory messages, I have to publish in NED frame, or else there will be confusion. Here I'm publishing timestamp. This is an array, float 32 array. So position, I'm publishing XYZ, my 3D position in space, XYZ. Velocity, I'm publishing meters per second. Acceleration, I'm not publishing. Jerk, not publishing. And I'm publishing yaw. Yaw is in angles, and make sure this is in Euler angle of desired attitude. Okay, so yaw is in angle. If I want my drone to rotate by 90°, I'll publish a yaw of 90°. There is one more thing as yaw speed. Yaw angle and yaw speed is different. Let's quickly see this, because this causes a lot of confusion later on. What is the difference between yaw speed and yaw angle? If I have this frame and this is my Z axis, and if I want to rotate my drone by 90°, and if I give yaw as 90°, my drone is facing here, my drone will start facing here, and it will stop. It will rotate at 90° and it will stop. But there is something known as yaw speed. That is, I want my drone to rotate at 90° per second. Now every second it will keep on rotating by 90 degrees. So it will keep on rotating at an angular speed of 90 degrees per second. That is nothing but yaw speed. While teleoperating with joystick, we will use yaw speed, wherein when I'll move the throttle, when the throttle will be in center, yaw speed, when the throttle will be in center, yaw speed will be 0. As I move the throttle, this speed will start increasing from 0 degrees per second to say 90 degrees per second. So here it might be 1 degree per second, 2 degree per second, 3 degree, and so on to 90 degree. So initially my drone will move slow, then it will move fast. This is the difference between yaw and yaw speed. And let me quickly explain the difference between NED and FLU. Why do we need two of these things? NED is, where is north? This is north, this is east, and for example, this is down. So Z is down. Okay, and FLU is front is X, left Y, and Z is up. This is FLU. So when I refer to as body frame, so for example, if you guys saw that for trajectory set point, it accepts set points in NED coordinates, NED frame. So when I ask my drone to go forward, it will go forward like this. Hai. Okay. And when I ask it to rotate by 90°, it will rotate by 90°. Okay. Then my drone. So right now, when I asked my drone to move forward, my drone head was facing here. But when I asked the drone to rotate 90°, my drone head is facing here. But when I send again, I want my drone to move forward. So intuitively, what do you want? Where should the drone move? Intuitively, if I am controlling my drone, I want that my drone, his head is looking this side, and I press the forward button. Ideally, the drone should go like this. Intuitively, this is how intuition tells us. Okay. But in NED frame, when I press forward, its head is like this, but it will go like this. Instead of going like this, I turned it like this. Now it should go like this, but it will go like this. That's NED frame. So while teleoperating, we use FLU frame, which is the body frame of drone. In FLU frame, if my drone rotates like this, and still if I press the forward joystick key, in this direction, drone goes forward. This is basically the headless mode, what we refer to. If I again move the drone's head like this and I ask my drone to move forward, it goes forward like this. Just like taking an example of your car. If you have a car like this, of course, car cannot drag sideways, but if I have a car like this and I ask it to move forward, it will move forward. Then when I rotate it, moves forward in the direction I have rotated. That's intuitive. Now, how would it be that I have rotated it like this, and when I'm sending forward command, it is going sideways? Car cannot go, but drone can go. So this is NED frame. We need to do some conversions here, and this is FLU frame, which we will be using for control. And while publishing, we will convert the FLU to NED and publish the set point. Any doubt? Or it's clear? No doubt. Is it clear? No means no doubt, or it's not clear? Clear. Okay. Okay. So we have seen what is your speed. We have seen what is your is angle. Your speed is angular speed. So we have seen what is messages. Now let's quickly go and see PX4 offboard control. I have created a package, a Python package named as PX4 offboard control. In that, I have created two folders, config and launch, which we will be looking at. Since it is a Python package, it also has a folder named PX4 offboard. I will go inside this. I have 4 scripts in here, which I have written. For now, we will go to position offboard control. This is a very lengthy script. I'll quickly explain it. And since most of you guys are familiar with ROS2, I'll not go into the depths. I'll just explain the logic. Here, we are using PX4 message types, and we will be using offboard control message, trajectory set point, vehicle command to command the vehicle. And we will be using vehicle position and vehicle status. Vehicle position will tell us the position of the vehicle, X, Y, Z coordinates, current, and vehicle status will tell us in which mode vehicle is. Is it in manual mode? Is it armed? Is it disarmed? Is it in offboard mode? It will tell us the status. Vehicle command we will use to publish data to vehicle command to move the vehicle. Trajectory set point, velocity position, offboard control, just to keep the heartbeat on. QoS profile, we had discussed that we need to match the QoS profile of PX4. So this is the QoS profile of PX4, which we are matching. We are creating publishers, as we have discussed why there was in and why there was out. In was PX4 takes in, out PX4 publishes out. So in, I use ROS2 as publisher and publish to PX4 to take input. Out, I use ROS2 as subscriber to take input from PX4. So in here, I'll be publishing offboard control message, QoS profile I have mentioned here while creating this publisher to this topic, trajectory set point, vehicle command. We will be publishing vehicle command, and I will be subscribing vehicle status, and vehicle local position from PX4. Again, I have given the callbacks as this, and QoS profile matches PX4's QoS profile. Okay, these are the few variables I have created. Set pointer, as we had discussed, when we transition to offboard mode, we do not just send one heartbeat. We initially warm up the signal. So set pointer is there to warm up, so that at 10th signal, we ask to engage offboard mode. That is why set pointer. This is local position variable. This is vehicle status variable. And this is takeoff height. Again, this is -5. Why I have given? I want the drone to go at 5 meters height. But since it works on NED, Z is facing downwards and ROS, Z is upwards. So in ROS, I want the drone to go up, I'll have to give it -5. Hope you guys are understanding that my drone is here. My drone is here at ground location. If in PX4 I give -5, then my drone will go here. So -5 in PX4 is up and +5 in PX4 is down. However, ROS2 it's vice versa. So I'm giving -5 in ROS2 for the drone to go up due to the frame transformation. Okay. 10 hertz, we are publishing the heartbeat, create timer 0.1, and every time after every 0.1 second, we are calling the timer callback. Here, we are calling the vehicle local position callback. That is every time I'm updating as my drone moves in Gazebo, this function is getting called from the callback when it is subscribing. And the local position is getting updated and the status is also getting updated. The current status of my drone, is it armed, disarmed, offboard mode, panic mode, manual mode, whatever. There is no such thing as panic mode, I guess. I am using that word. Okay, so there is manual mode. Vehicle local position, I am getting continuous feedback loop. Where is the drone right now? What is the state? Arm, these are commands which we use. Vehicle command, then we use this command to arm the vehicle. This is again, you do not understand what is happening. This is just how things are done. In PX4, there are a lot of parameters to be tuned. When I want to arm the drone, I just do param1 as 1, so drone will arm. If I do param1 as 0, drone will disarm. Okay, and where will you find this message type? Let's see what I'm talking about. Let's go in vehicle command message type quickly. Vehicle command message. Here you can see such a big file. So I hope though you don't try to understand this. You just try to learn how this works. There are so many parameters in PX4 that you can tune. Yesterday I was going through it. All these commands. So depending on your need, you can explore them. We will be exploring a few. I showed you just that there's nothing of understanding in this. It's just that this is how it's done. For arm, I do param1 as 1. For disarm, I do param1 as 0. For my vehicle to go in offboard mode, I do param1 as 1 and param2 as 6. This tells PX4, okay, user is requesting offboard mode. If all three pillars are satisfied, give him access. Land is again, this is the command vehicle land, which PX4 does what it does. The moment it receives that command, it starts the landing sequence. Here is publish offboard control heartbeat. We saw offboard control message. Right now we are concerned with position. We are sending position. All the rest are false. We saw the message type. These were the message types in there. We saw that. Publish position set point trajectory message. Again, we saw this. What we are doing here, we are asking the drone to go to 5 meters up, and while going up, rotate by 90 degrees and stop. Publish vehicle command. This is what you are publishing. Vehicle command, the params and all these things. You are sending the drone to do whatever it is supposed to do based on your code. Okay. Again, this is nothing. This is how it is done. It is receiving the command. Publish vehicle command. It is receiving the command. You see, we are calling this function here, publish vehicle command. It is receiving this command. Okay. User is asking me to land, just land. So here I have passed the parameter command, and here we have passed the params, this thing. And so here we can, instead of passing 2, if you use double asterisk, you can pass multiple at a time. So here I am passing param1 and param2. So based on that, it is switching modes. So this is the function for that. Timer callback every 0.1 second. That is at, is the workshop done? Workshop is not done, man. Workshop is remaining. We will try to wind this up by 6. Uh, and which workshop are you referring? The previous ones are done. Recording is available. This one is not done. Okay. Okay. So timer callback. Timer callback every 0.1 second. Timer is getting called. What are we doing inside that? Sending offboard signal, heartbeat, clear. Warming up, clear. Moment it gets warmed up, I'm asking engage offboard mode and arm the drone. Arm function we saw using the arm command above. Here it is checking if vehicle local position, that is if vehicle local position dot z, that is if z is greater than takeoff height. Takeoff height we have given as -5. And when the drone is at ground, 0 is of course greater than -5. So if vehicle local position is greater than -5, which is true when the drone is on ground, and vehicle is in offboard mode, that is our vehicle has gone in offboard mode successfully, start sending trajectory message to it continuously. So here in this published set point, I am sending XY as 0 and I am sending -5 here. Continuously go up, go up, go up. And every time when this callback is called, this loop is verifying. Drone will start going up, so Z value will start getting changed. From 0, it will become -1, -2, -3. The moment it reaches -5 or greater, this loop becomes false, comes in else if, it triggers landing sequence. So here you can see continuously that if vehicle local position is less than takeoff height is -5, and vehicle local position is less than -5, start coming down. That is either it has become -5, that is you have reached the top location, or you have exceeded that, start coming down. Moment land is initiated, PX4 gets to know that, okay, now land is initiated, let's take back the control in our hands. It puts you out of offboard mode. It starts the landing sequence, disarms on its own. In between, you cannot do anything because I have called land. So this loop will get false because the state will change moment land is triggered. And then exit 0, program will end. This loop will clearly end at once. This is the main function. Okay, hope you guys understood. Um, let's quickly try and run this, and then if you guys have any doubt in the code, I'll get back to the code once again. How do we run this? Very simple. Run the PX4 SITL, run the DDS agent, go to the go to PX4 workspace, do callcon build. I had already built it, so source the workspace, and now let's run ROS to run from PX4 offboard package. Let's run, what was the node name? Position offboard control.py. Here you can see now. Okay, let me put this here. Here you can see drone will arm, start flying, go to a specific location, start landing, disarm. Here you can see continuously set point is getting published, drone is arming, current Z value is changing continuously. Here you can see value is changing. The moment it reaches -5, drone sees that, okay, I have reached the maximum height, let's start landing sequence. -5 reached, almost reached, land mode enabled, drone started landing. Now PX4 is taking charge of it. We are not taking charge of it. Landed, disarmed. So now we were successfully able to control our drone via the offboard mode from ROS2 itself, wherein the drone flew, reached a specific height, landed. A complete loop. We sent a message, got the current updates. These were the current updates getting from the drone. Based on the current updates, we did what we were supposed to do. Uh, do you guys have any doubt till here? Okay. Well, in that case, code is also understood. We have seen this. We have successfully, now we are able to receive location, status, sensor information, everything from a simulated drone. So using ROS2, we are able to read PX4 data. And now we can send position commands as well to the drone using ROS2 node. So we can write as well. So this is a full package we have created. Let's move on to the final project, offboard velocity control. Till now, we controlled our drone using position. We asked it to go to 5 meters and then come down. You guys can experiment, and where I was giving 0, 0 as set points, you guys can give 2, 3. So drone will go forward 2 meters in X, 3 meters sideways, and 5 meters above. You can even try and improve the conditions and try making a square or a circle using a for loop, using that drone, using the position commands. You can experiment that and maybe post it on the group or somewhere. Okay, let's move on finally, joystick integration. So we use the standard
Okay.
ROS to,
Hello.
yeah, hello,
I have a doubt actually. Is it already if I ask you now?
sorry, you have a
Hello.
doubt, you can ask. Yeah, you can ask your doubt.
So okay. We have been sending first of in the workshop so far. We have sent set points to the drone, correct?
Mhm.
So were those set points actually in the flight path, or did we just give a specific set point at a, let's say, a target altitude, and
Yes.
then the drone reaches that altitude, then we give it a set point in X and Y with the Z
Mhm.
keeping the same value, or do we have to
Yeah.
map it out, or do we have
No,
to give each point along the way?
you just give a set point, drone will go there automatically. Just that you have to, just like I showed, every time you have to keep telling the drone go to this set point. Right now, when we were giving 5 meters, so we were continuously telling go to 5 meters, and the loop was also like increasing. You saw this,
Right.
right? This thing was changing,
Yes, yes.
and when finally it
Right.
reached 5 meters, it stopped. So you just give a specific target position, drone will reach there on its own. Okay, cool. So position control is done. Now we will quickly look at um, joystick. So I'll quickly explain the joystick code. This is a low level code. Uh, uh, Basically, when you use teleop twist joystick package, it does this for you. But I was initially using teleop twist package, but um, in teleop twist package, you don't get access for Z axis. It is mainly meant for 2D AMRs and all those things. So I had to remove that and directly interface with the joy package and joy topic. So what is this code doing? Here I am defining the joystick axis. Now how will you know what the joystick axis is for you guys? I'll quickly show it. This is the joystick. You guys can see it here. How will you know that this is axis 1, this is axis 0, and all those things, and which button maps to which? So there is a software or tool which is known as JStest GTK, this one. The moment I connect my joystick here and refresh it, it sees that this joystick has been connected. If I open this, now you can see when I move my joystick controller forward, then it is changing. So this one is mapped to axis 1. This thing is mapped to axis 0. Similarly, this one is 3 and this one is 4, and these buttons, you can see these buttons, you can see these buttons are mapped to these numbers. So this is how you can find for your joystick what is the mapping, because every joystick mapping will be different. So here using the joy node, which is the default node, which we installed the joy node package. You guys have to install that. Using that joy node, I have, and this JStest, I have mapped these joysticks. I have mapped the buttons here, And we have mapped the XY velocity, not mapped, but given a limit that I want my drone to move forward or sideways at a maximum velocity of 0.8 meters per second. And I want my drone to, the yaw speed I have given as 1.5 radians per second. And hover, when my joystick is at the center, I want the drone to hover. When I throttle up, it should throttle up. When I throttle down, it should come down. Or else when it's center, just hover at 0.5 meters per second speed. Okay. So, and how is it hovering at 0.5? This has been taken care in velocity control, offboard control, that we will look after this. Axis dead zone I have defined, just like my joystick is new, so there might not be any fluctuations, but for people who are using old joystick, there might be fluctuation. So it will not show 0, it will keep on fluctuating between some values. So based on your joystick fluctuation, you can increase the dead zone. So I have kept 0.1 after hit and trial, axis dead zone and throttle dead zone. Then we have this joystick here. You see PX4 QoS profile we are using to subscribe and publish to PX4, and joystick, the joy node which we are using. Let me show what the joy node is exactly in the launch file. If I go in joystick, this node you have to install. So basically you have to install which package? You have to install the joy package, and from that you have to run the joy node executable. So what this node will do is that it will get the buttons, the low-level buttons you have pressed on the joystick, and publish and map the buttons to the joy topics, from which our code will get to know that the user has pressed these buttons, and based on that we can do whatever we want to do. So the joy node topic uses this QoS profile. It doesn't use transient local, it uses volatile, and similarly reliable and keep last. Okay. Here we have created these publishers. Offboard velocity command, that is whatever velocity I am calculating, I'll be sending to my velocity control top node, which will be controlling the drone velocity. And this is the arm message. When I press A on my joystick, my drone will arm. When I press Y on my joystick, my drone will disarm. This is just a Boolean message, true or false, that is if the drone is armed or not. Okay. And here I have created a subscriber from where we are subscribing to the joystick topic, the buttons which are getting pressed. Here we have armed. Initially we have set everything to false, and then all the speed has been set to 0. Okay. And then here we are just printing the instructions, and a joystick is running at 20 hertz, that is 0.5. It can even run on 10 hertz, but better it runs on a higher frequency so that control is more smoother. Okay, so this you can read which stick does what, and you can map it accordingly. Apply dead zone. This function is just to apply the dead zone so that fluctuation is not there, fluctuation is removed. Okay. This is the throttle axis. This controls the throttle, and again it is mapping to the dead zone. That is, initially in my case, when I read my throttle, my joystick outputs between -1 to 1, but in some cases it might happen that joystick can output some other value. Okay, so for that, to make things standard, I have made this thing so that it maps whatever value, it maps to 0 and 1. Okay, so say if my joystick is at center and axis value is 0, so it will send 0.5. 1 divided by 2 is 0.5. That is, throttle is at 0. That is, drone should hover. And the moment I increase it, it will send positive value. I decrease it, it will send negative value. Okay. This function, joy callback function, it is reading the button presses and whatever key sticks, whatever you are moving. This joy callback function is handling that at low level. Here you can see when I press button A, I'm sending that drone should arm. Okay, so I'm sending the arm message as true, that okay, arm the drone. When I'm sending X, so when you press X, the drone will start hovering. That is, when you increase the throttle, drone won't go up. If you decrease the throttle, drone won't come down. This is what this X button is supposed to do in here. Y is for disarm. Okay, and these are the access handling this thing wherein I have given Vx raw, that is velocity in x direction. For example, when I move my joystick like this, I want my drone to go forward, backward, sideways like this. So this is y, this is x. Whatever you wish, you can map. And this is the final after applying the limits, that is 0.8 meters per second. I don't want that drone should go faster than that. Similarly, I am calculating the yaw, and then this is for throttle and auto hover. And so basically left stick down, throttle. So what it is that when the drone is in center and I'm throttling it up, so initially when the this thing will start, drone will start flying. So initially I'll have to reduce the throttle to bring it to 0.5, then only it will start um, hovering. So in some cases it might not be the case with joystick, but there is a keyboard teleop which I have. So in keyboard teleop, the drone, the moment it gets armed, it will start flying. So you have to press the S button to reduce its speed and come to 0.5, so that drone hovers at 0.5. Okay, so these are nothing but the mappings. And finally we are sending the Vx, Vi, Vy and Vz data, which is, this is pitch, no, this is roll, this is pitch, forward, backward, this is left, right, this is up, down, this is your rate, that is the drone turns, and this is throttle. We are sending that, and here we are mapping all those things. Okay, we are running short on time, so we are not going into this, but these are very simple. You can just put in the values and get to know what's happening. Publish velocity, then again we have the publish velocity function wherein we are publishing twist velocity. We are converting the joystick mappings and publishing it as twist velocity. So linear x, we are publishing x, y, z, angular z, we are publishing as yaw rate. In PX4 we don't publish angular x and angular y. For example, if I want my drone to move forward, then maybe I can publish angular y, so my drone will move forward, but I just publish the speed. PX4 calculates the angular turn which it needs to move forward on its own. Okay, and again this is for removing any fluctuations in the joystick, and these are for button pressed, whatever button is pressed, these are callbacks, and this is the final script. So this is nothing, this code is nothing but taking low level inputs from the joystick and converting it to command velocities after applying limits and removing fluctuations. So this code has been written after a lot of hit and trial. You guys are seeing the final code, which is looking very complex, but I started with a very small code, and then a lot of hit and trial went into it. Okay. Finally, let's look at the velocity offboard control. Everything is the same, just like position offboard control. Just that in here, we are not sending position, we are sending velocity. So these are the limits set here. Okay. And we are subscribing from our joystick node, that is offboard velocity command and arm message for arming and disarming. And then these we have already discussed, vehicle status and all these things, armed, warmed up, yaw, vx, vy. These things we have discussed already. Status callback, this is the function which tells us the status of the drone, in which mode the drone is, arm, disarm, offboard, manual. This is the attitude callback. This here, q is equal to message.q. In ROS2, we don't use Euler angles, but we use quaternions. So here, even in PX4, so here message.q, 4 quaternion values are getting stored in it. We are checking the length 4, and then here we give the values individually, w, x, y, z. Okay, and from these quaternions, using this function, we calculate the yaw angle. Okay, then velocity callback. This is the twist message getting from the arm command. Here we are mapping the velocity, whatever we got from the joystick, and storing this in a variable Vx, Vy, Vz after putting the limits so that velocity doesn't exceed the value. You can just put in values like this and manually dry run it. I'm not doing that because we are running short on time. So here we are starting the offboard mode, then arm callback. This is the callback function used for arming the drone. So what here we are doing is that when message.data, we are seeing arm message. We are subscribing from this topic. I am pressing A on my joystick. I am telling my joystick arm the drone. So this arm callback is getting called. This velocity node subscribes from the arm callback arm message. Arm callback function is getting called. Message.data, if it is true, because that's a boolean data, if it is true and drone is not armed, then arm it. Okay, how do you arm it? You start the offboard mode, prepare for offboard mode, wait for 2 seconds, and then you start publishing this command for arming the drone, and then you publish drone is armed. Let's see this function once. Start offboard. So what's happening here? Initially, we all know that we have to warm up the heartbeat and the controller PX4. If it is warmed up, then return, then don't enter in this function. It is already in the offboard mode, but it is not warmed up. And since we want to start the offboard mode, then here we are warming up. Here we are running a loop wherein we are continuously sending the heartbeat. Publish mode is sending the heartbeat, and then we are continuously sending the set point. We discussed that we have to continuously send the set point. These are dummy set points. So once PX4 recognizes that both the two pillars are there, arm it. So here, warmed up is true and drone has been armed. Warmed up is true, start offboard. The moment we will come here, arm callback, start offboard. Okay, it waited for 2 seconds. Then offboard is there. Now we armed the drone. We send the request to arm the drone. Okay, and similarly, we are doing it here. Micros is just to keep a record of the time. Publish mode is sending the offboard command, the heartbeat, which we had looked. Publish set point we looked at. It is sending. Nan stands for not a number. Since we are not interested in position anymore, XYZ we are sending as nan. We are interested in XYZ velocity. So we are mapping the velocity Vx, Vy, Vz, which we are receiving from here. And all these things again we are sending as nan. We are not interested in yaw, we are interested in yaw speed. What's the issue with yaw is that you turn your joystick, drone rotates to a certain angle, then stops. I want that I keep my joystick like this and drone keeps on rotating, just like how real drones do. So that's that you can achieve with yaw speed. Then you have publish command. Again, this is publishing the velocity commands, which we looked with the command and the params. Here the params are getting published. Then we have start offboard mode we just looked at. This is the final loop which the timer is calling. So it is recording the current time. It is sending the heartbeat, which is publish mode. It is seeing if it is in offboard mode. It is in offboard mode, then offboard mode is active, else it's not. Okay. If not in offboard mode and not armed, then publish set point so that it gets armed. Okay, because heartbeat is already being sent, so I just need to send set point and return unless and until it enters offboard mode. Now here I am checking that, so this code has been done in such a way that if there is inactivity, drone will start landing. So here I am checking for inactivity greater than 0.5 seconds, and once if that is there, every velocity is 0, drone will start landing. This we do for frame transformation. As in the beginning, I had mentioned, for intuitive control, we control drone in FLU mode, and but while sending trajectory set points, we need to convert that FLU coordinates back to NED coordinates. This is how this is being done here, WX, WY, WZ. Okay. The maths, you can look for this on YouTube. There is a very good video which shows how to do the math behind it. And then finally, we are publishing the set point X, Y, Z in NED frame and the yaw speed, which is the angular speed of the drone. And then again, we are just what do you call printing the yaw speed, and also we are removing the fluctuations by seeing that if yaw speed is less than 0.01, don't do anything. If it's greater, only then send to remove the fluctuations. This is the final main code. Similarly, okay, let's try and run this first, then we will come back to any doubts, and we will look at the keyboard thing. So for this, uh, in order to not start PX4 every time, PX4 SITL and all those things, so I have written a launch file here which starts PX4 on your behalf in a genome terminal, and it also starts Micro XRCE DDS agent. And since we have to use joystick node and velocity node, I have written in one launch file. This launches the joy node, joystick teleop node, and the controller node, the velocity control we discussed just now. Let's try running it once. So now I need only two terminals, and both terminals I'll go in PX4 ROS2 workspace, and here also I'll go in cd PX4 ROS2 workspace. I'll do source install setup.bash. I'll do source install setup.bash, and then here I'll do ROS2 launch. In it, I will launch PX4 bring up package. In that, I launch minimal.launch.py, and here I'll do ROS2 launch from PX4 offboard package. I want to launch the joystick teleop launch. I press enter. It opens a terminal in which PX4 runs. It opens another terminal in which XRC DDS agent runs. This opens Gazebo for me. Drone is there. Now I run the launch file. Okay, now you can see. Now let's see if things work. Now if I press my A button, if you can see, this is my A button. If I press this, drone should arm. My drone is arming. Now this is my throttle up button. If I increase this, here you can see it is throttling up, but the moment I left it, it came to 0.5. So it is now hovering. It is not going anywhere. If I want to make it go up, I can make it go up. Now, if I move it sideways, it will go sideways. Okay, no, this is for yaw. So here you can see yaw speed drone is rotating like this. It is rotating like this. Okay, now this is for forward. Now my drone is moving forward. My drone is moving back, left, right, center, and if I throttle down, it will disarm, and then I press Y, it will formally disarm, and then if I press A again, it should arm back again, and then when I do throttle up, it should come up, and now it is hovering, and now I can control my drone any way I like. Now you can simply move your drone. You can control your drone any way you like. Okay, so this was the final project. You can also try running this script if you don't have a joystick. I have this script as well written. Teleop keyboard. Using this script, you can control your drone via the keyboard keys, the arrow keys and the WASD keys, and you use space for arming and disarming. So what you do is the moment you press space, it will arm and start flying up. Then you have to keep on pressing S till it reaches 0.5. Moment it reaches 0.5, it will start hovering, and then you can move it anyways you like. So keyboard, exactly the code is same as joystick, just that in keyboard we are taking input from these key values. We are reading A, B, these are for arrow keys. We are reading this, and based on that, we are asking our drone to move up and all those things. The code is very simple, and then twist command we are doing. And this is for throttle and hover. So for this, you don't need to run any external node. Like in joystick, you have to run joy node, but in here, that's not required. So this was the final project demonstration, and now we have seen how to teleoperate our drone in Gazebo using a joystick, and now using our hand we can take the physical input. Joy node will convert that input into button presses, and then we feed it to our script, and then the script does what it's supposed to do. Take the input, convert that to command velocity, feed it to velocity controller node. Velocity controller node sends the message to PX4 via the Micro XRCE DDS agent that receives, moves the drone, sends back the sensor data back to XRCE DDS agent, ROS2 subscribes the state and location from it, and based on that, it hovers, and whatever it does in Gazebo. This was the entire pipeline. We successfully completed the workshop on time. If you guys have any doubt, just let me know if there is any doubt in the code or wherever. I can quickly cover that. I went a bit fast in the coding section. I usually go slow, but as you saw, the code is very long. And if I go in the nitty gritties of it and I start doing dry run, then the video will become very long. So this workshop was mainly towards showing the pipelining of things, how you can integrate the two things, which I think we did successfully. Just need to learn and do it and see. Cool. So the next steps, the recorded video will be uploaded to Mechamind Labs YouTube channel. People who have not subscribed, go and subscribe to it. We give updates there. And if you are not a part of the WhatsApp community, we have pasted in the chat box, and even this PPT will be available. So you can click on this links and join the WhatsApp community as well. So till here, you guys understood everything. How was the workshop? Very fast, slow? If you wish, anyone can unmute and now say something. How many people are there? 1, 2, 3, 4, 5, 6, 7. So guys, we have completed our workshop on time. If we would have taken a 15 minutes break, then it would be exactly 6 p.m. Since the break was short, so it got completed 8 minutes earlier. So I hope you guys enjoyed the workshop. So to subscribe to the channel and join community. And if you guys are interested in building a physical robot from scratch, so do join the waitlist, and we'll be conducting a 45 days cohort training program soon, wherein everything will be covered from scratch at a very slow pace. So yeah. So the workshop is officially over. We can end the meet now if you guys don't have any questions.
Thank you so much. Thank you so much.
Yeah, welcome.
Thank you, Utkarsh.
Yeah, welcome.